Hello, welcome to this stream. Today's stream. Yesterday we took the Icebreaker VGA module, Pmod module right here, connected to our ARTY board, took their Verilog file online, dropped into a block diagram, hooked up all the necessary signals for the ARTY board, and we got the VGA to work. And we can show you a quick demonstration of it on my monitor here. I have to move the camera. There we go. Blue, red, magenta, green, cyan, and yellow. And line testing, and we're gonna let it go through the demos it has. Bar, there's like a little ball as well. So let's go look at what resolution is this. So we can go down to information on the monitor. We can see that it's 800 by 600 at 60 hertz. We're gonna up that to 1080p. So we can get 1080p by 1920, 1920 by 1080p. So that's the goal by the end of this stream. Okay. So let's get that back to my streaming tools, because that would actually be useful. And there we go. That's the audio board we're working with. So let's get to it. The first thing, let's up the clock to the correct speed. So using this thing, we're going to use a 148.5 clock. Let's drop into here. Where's my clock? Here's my clock generator. Output clock. So we want 148.5. Enter. We have 148.5. So easy. I have to close this window because we have to get a resolution so you guys can actually see this. Okay. Next, we're going to have to dig into this and change it. So first, let's look at the VGA core. I am curious to see if they have any parameters for the size. VGA ball. How do you determine the edge? D decimal 120. That's the color. The X position, Y position, X position, Y position. Start in the center of the screen. Direction. Here we go. We won't change this, I guess. Let's see. How are we determining this? But how are we determining when we print it out? Frame, line, frame, line, frame. Okay, so it's using all the data there. So yeah, let's go see what happens when we just go change the parameters in VGA timing. So I mean, we're just gonna copy this, right? And do a dot star, a star slash, and yeah, let's see what signals we have here. So let's see if we go to the 8060 and just get what these signals are. Here are the 8060. Active is 800. 40 is front porch. Sync width is 128. Okay. Back porch 88. And the blinking in there. I think we just assume there 1056. Okay, let's go down here. So active pixels. Oh. Okay, let's make sure that I can fit to that bit real quick. Over here, we're gonna do decimal. We're gonna do 1920. Yeah, that fits 16 bits fine. Cool. So sync width is 44, which is this right here. Front porch is 88. And back porch is 148. 148. And then we only care about the total, which is going to be 2200. VSync is 5. Back porch is 36. What we got for the front porch is 4. And active is 1080. 1080, and total is 1125. 1125. Okay, let's refresh those modules. I'm gonna go back and see how they do the bars here. RGB line. We have a new follower. Hello. Welcome. I don't see them in the chat. Okay. RGB line. Anything else that determines the line for the RGB data? Hey, what's up? Okay, so welcome to the stream. We are looking at doing 1080p 60 frames per second on the ARTY FPGA. What's your experience with FPGAs? So it's gonna be timed. Whatever, so we're gonna see if we can produce 1080p, then we just have to look at doing our own thing. Let's go ahead and generate this. So I'm probably going to make a VHDL module that takes a AXI stream input and outputs this video. Do we want to configure resolution? We probably should just have like being able to reconfigure resolution, right? Some parameter that goes through all these things. That's gonna be interesting. Okay. Oh, that sounds fun. Yeah. I mean, I've done some soft processor experience with some RISC-V stuff, MIPS and ARM actually. My university classes have explored different architectures that I've been able to attend or TA for. This take too long to build this. Oh. So After that's built, we're on to implementation. That shouldn't take too long. We're gonna have to rewrite this core. This core is just doing colors. We'll need to take data into from a FIFO. That's gonna be fun. I probably have registers for these different settings. That'd probably be good. We'll probably do a state machine that and it's just determined upon those values what happens, receiving data or not, and then we just have a new data coming in from the actually stream port. We're doing 12 bits. We can do 3 pixels at a time. Oh, but I was going to process it at 24 bits so that we could save the image. Okay. The goal here is to have Ethernet UDP stream a video here. We're going to process the video in actually stream format, output the video over HDMI, and also output the video back over Ethernet. We may not be able to do 1080p effortlessly over the FPGA, but we'll have to see. Oh, we're gonna get the right bit stream state. We'll find out if this works or not. What about net timing? Did we have any concerns about timing? Looks fine. So let's see. You can open up in PowerPoint, right? So what we want to do, we need some clock domains. How do we handle the other clock? We're going to need a dynamic clock if we want to do multiple resolutions. I mean, that might not be something bad to look into. So we're going to have like a timing core here. We're going to have a async FIFO. This is going to be actually stream here. Stream be 24 bits, and we're going to have 8-bit data here. 8 bits. But this is gonna be a different clock domain, right? And can I show, like, I guess we could do like half shape effect. Can I like divide it down to half? Shape, fill, gradient. We can do a gradient. Yeah, we can totally do a gradient. More gradients. Let's do gradients and delete that, and then we can just color blue. Right, which direction? How do we do a direction? Direction, we want to go like that. And we want to take this color and we want to make it green. There we go. Make that green. So if we want to do controls, we're going to have to do controls probably in a different clock domain. Right, so, and then we're going to have we'll call it orange. This is going to be axis light command interface. Instead of FIFO, we can probably do a double register. Double reg, gradient, down. This is going to be orange. And we can then oops, another arrow, green there. So that's, I guess, kind of our plan, right? So the orange clock is, we can insert some text boxes. This is going to be 100 megahertz clock domain. And then down here we're going to have 142. That is to process the data at the clock speed we can do. And then we're going to have here, this is going to be kind of a dynamic clock, but max 148.5 in kind of this green domain. Okay. Oh, we can do that. Okay, let's see how our yeah, let's use this guy. We're gonna program DVI. Yeah, sure. So it's working, right? Well, let's turn it on. Look at that, 1080p, 60 hertz frame per second. Should have probably brought over the screen, so I'm going to attempt to point the camera at it and hope you can see. So there's some issues here because, as we can see, it's kind of doing all the demos for the 8060 view, but that's just data input. We can easily change that out. But here we go. We have 1080p, 60 frames per second using this board right here with this Pmod. Let me change the screen back. So, should we just build from here? Maybe do a new block diagram afterwards and just have the old one as a reference? No, let's do a new project. We're going to do a new project. That's it. We're going to have a new project. We're going to call this DVI_1. We're not going to specify anything. We can go to ARTY, finish. No, we don't want to close that current one. So, yeah. First thing, I'm going to make this VHDL. I'm a VHDL programmer, prefer it. So next we're going to create our IP core. And to do that, we're going to go to Tools, Create and Package New IP Core, and we're going to call this DVI stream. Cool. Anyway, I don't really care about those values. So we're going to have an AXI light. We're going to need at least 16 registers, so I always like to do double of that. Always do double what you think you need. That should be sufficient for that. We're going to add an interface. This is going to be a stream. It's going to be a slave. This is where our video data is going to be coming from. And what we're going to do at first is we're going to set it to a solid color. And we'll add a GPIO kind of port or something like that where we can change the solid color of the device. But right now, yeah, we're going to set that up, and that should be sufficient. I mean, 32, yeah, I don't think we should need to change that. So yeah, let's try to figure this out. So first, let's just kind of do our generic user inputs here. We're not going to worry about user parameters because we're going to have a dynamic clock. So what we're going to type here is we need a, we're going to call it a pixel clock. And pixel clock is going to be inputs. And then we're going to need the red, green, and blue outputs. Red out, standard, logic, vector 3 down to 0. Get plenty of those going. And let's look at our other design that we have floating in the background to figure out what the other ports are going to be. Diagram. VGA active, sync, and V-sync. Well, the clock we should just be able to pass through just fine, because the clock, even though it's an input, we can just pass that out through an output. I guess we could make it kind of streamless and connect it to that clock period. Nah, I don't like that. I don't like the clock coming out. The clock should be able to be sourced externally. So let's do active, H-sync, and V-sync. And probably just call that active, standard, logic. And standard logic, and let's get 3 more. We're gonna call it H-sync, V-sync. Okay, so these are gonna be our standard outputs. Yep. So next thing we want to do is we want to edit the stream. So we're gonna have some user ports here. User ports. User ports. And we're going to want the same signals that we got from VGA timing. We basically want those. So let's just, I guess, copy that for now, and we'll just deal with it. Okay. Do some multi-line editing in Vivado. That did not work as I expected. Nope. What's that? We can do it that way. And then we need out standard logic vector 31 down to 0. Okay, cool. So we have those ports. We can go down to our Axi bus interface here and go ahead and add them. So we're going to want that, and then we're going to want to copy these there. Don't need that. Get rid of that for this. There we go. Oh, whatever. I'll just I need to learn. I wish there was a beautify in here. So I was saying those don't really exist, which I mean I understand. So we'll go to right here and signal. Standard logic vector 31 down to 0. So okay, this is happy. Let's take these, drop down to our Axi interface right here, Take that to our user port section. Go down here, and we'll just make it the slave register. So make it super basic. So we'll just go. One, 2, 3, 4, 5, 6, 7, 8, 9. We got 10 values. And we're good to go. So we have our configurability over actually stream. So our but we wanted to double register it. Where should we double register it? We should probably double register it here. So what we're gonna do I don't want to do a block. So let's do a VHDL blocks. I like those. VHDL block. We're going to do a block statement here. I find blocks very useful. We're going to get rid of those things. This allows you not one. Yeah, get that. This way we can kind of assign signals here. We're going to call this double reg. Nope. So we're going to take these register signals and we're going to assign them here, or establish them as signal. Why is it? Oh, I'm supposed to do it like this. Signal standard logic vector, everyone down to 0, and then we're going to okay, so then we need a process. And we want these to be in the scope of the block, right there. And then we're gonna need a process. And we're just actually gonna steal, just go ahead and steal this process right here. And if you don't need a reset, don't assign a reset. That's an important thing in FPGA design. Resets should only go to registers that matter. And since these are registers that are constantly being updated every single clock cycle, we can completely ignore the reset. And we can just go, we don't want those ones per se. So we want to go like that. Why does it grab those extra signals? I do not know. I'm gonna grab them. So there's one layer, and then we're gonna add the second layer. So there we go. We have double register it. Oh, we're supposed to double register it in the clock we're using. Okay, yeah. So we're gonna add pixel clock to this guy. Pixel clock. In standard logic. My bad. I'm using the wrong thing to double register it. Double register into domain that's reading it. New pixel clock. There we go. Back down here. This is all happening in pixel clock domain. to get some nice, good double registering happening. So when the signals come out, they will be in pixel clock domain. To do that, we also need to add pixel clock to our upper port connections. So let's go here, add pixel clock. I think we can just say pixel clock, pixel clock. Okay, so we're good. Now we need to write the timing core, and for that we're going to have to add some new HDL. And this HDL is going to take in the pixel clock, the configuration registers, the data, and it's going to output the colors when it needs to. I mean, basically when it's not blanking, when the active signal is high. I assume that's what's happening, right? I mean, let's go look at the other project real quick. Not that one, this one, right? So this outputs bid active, and when it's both of those are active. I mean, we might just be able to drop this core in there, you know, but I don't know. I think it'd be easy to write. New frame, new line. State machine. Oh, they did an exact state machine like that. They define the states as such. Sync back active. And yeah, it just generates these things, and it's all we really care about. So yeah, we could probably generate this relatively easily. Let's see where these defines come into play. Let's look at and count h equals that, and count h equals that. I mean, we could follow a similar structure, but we'll probably use a different type of state machine. We can actually use some encoding with it's been a while since I wrote a state machine in VHDL, so we'll go ahead and do that. So yeah, let's do a new structure, and where do we put we assume the data is going to be already correct, and that the active, and then we could probably delay them a little bit, get some stuff going, and double register on the output just for good measure. Do a fall through. Okay, yeah, we can do stuff like that. Do a small asynchronous FIFO. We could potentially change the clock domain. Now let's just do a clock. We'll just do an asynchronous FIFO at this stage. So yeah, let us create a new source file. We're going to create a file. We're going to call it VGA timing, but it's going to be VHDL. VHD file location. It's going to be an IP repo. I mean, like, we're going to be in DVI stream. Click. Okay. Finish. VGA timing. We're going to have a good old pixel clock. So, I mean, input wise, we have all these control registers, but I can just copy that. Yeah, let's just do all the other ports on our own. Okay, so we have a pixel clock. Let's add the control registers to define different resolutions. So we have a pixel clock, we have different resolutions. They all need to be inputs, not outputs. Next, let's do kind of our handshaking for video data. So we're going to do pixel data, which is going to be an input. And we probably can just lower it 11 down to 0. We're just going to take the values we want from the FIFO. Make sure it's a vector as well. And then we're going to need an output, right? We're going to need a pixel read. We're going to be an output. Standard logic. And then we're going to need our generic outputs. Red. Okay, now we need our timing outputs, so we're going to have active. Logic. 1, 2, 3, get rid of that one. Call that HSync and call this VSync. Okay, now that we have so we need two state machines. We're going to have a horizontal state machine and a vertical state machine. And basically, when both vertical and horizontal are active, kind of like in this guy, when both up here, when both horizontal and vertical are active, we're going to implement the active. And when the active is implemented, we're going to register it. We're going to do probably double registers on the outputs, but then we're going to grab the pixel data and then we're going to output that active on the pixel read. And then, yeah, we should be good on data. And the pixel read should be low on when active is low. And then we just grab the data, while you register the pixel data twice, once and twice, and then we'll put it on the output. Okay, so now we need to learn how to do an enum and VHDL. And I've done this plenty, but I forget syntax like no one else. So we're going to just review how we do a state machine. So here we go. We got a state. We're going to determine a type. That is a good thing. We're going to call this H state and V state. So we have back porch, front porch, sync, and active. So the most important thing in this situation do we want a reset value? Let's see. We're going to reset. We don't have a reset input here. Well, we would just change the parameters and deal with it. So no reset. Cool. We just go on to the next frame. Let's see. I'm curious to how they handle. They reset. I'm fine with it, just dealing with it. Doesn't really matter per se, but what should we begin on? So it looks like they begin with the H sync. And so they do the H sync. Let's make the state machine sync back porch active front porch. That sounds good. Are the totals ever used? Totals are never used. So it's purely just counting these 4 different values. And active is high when this and this one are high. H sync is high when that one is high, and V sync is high when V sync is high. Yeah. So pretty basic. And we just, when does this determine a row? When does it roll over? Bid new line. Okay, so when the back porch finishes, we have a new line. And count V equals 2. Okay, when a rollover happens. So that's how they do it there when a rollover happens. And a rollover is oh, so they kind of start in the V-sync rollover period. Interesting. Doesn't really matter in the long run. We can just let a frame go off. Yeah, let's just let it run on its own. Okay, and basically start it in VSync. And it rolls over at the when H-sync starts. The new line begins. Going to their stuff. Okay, so let's go at it. So I think the important thing is to first create this horizontal state machine. I'm going to do the 2 process format because that's what I like. It's going to be a little bit verbose, but I've always enjoyed that style rather than a 1 process style that is shown here. Okay. Yeah, so let's go here. We have H state, V state. We're going to do sync, back porch, active, and front porch. Yeah, how he got active is already declared. So we'll just say H active and V active. So let's do another block because I like using blocks. So block begin and block. So we're going to do block H state machine begin and block H state machine. So signals we're going to need here. We're going to need state. State is going to be a signal. Signal state that is going to be H state. I'm going to default that to, I guess, sync. And then we're going to have a next state. This is where it's going to get carry. And we have do we have numeric in this file? We're going to get numeric, and we're going to have unsigned values. We're going to have signal unsigned. We don't know. That's not the correct syntax for that. Okay, so we're going to have a counter. And it's going to be unsigned. And we'll just go ahead and make it 31 down to 0. And the counter is just going to increment all the time. Does it really matter? I think that's one that I can put into the other process. I mean, we could do a next counter and just show how it works. And we're just going to be activating things. The VSync and the HSync. So here's where we're going to start having some signals that are going to be more global. So H active is going to be a standard logic. And we're going to have V active. And it's going to be into the read output right there. And we do signal H sync reg standard logic. And we're going to do 0, 1, 2 and spell logic right. Let's do 3 of those for VSync. So, and then we want active. We want signal active reg 1. Standard logic. Okay. And then we need rising edge. I mean, we could just check for the rising edge, and that could signal a new line. I mean, well, why not just do a signal H roll over? We can do that. Okay. Now that we have that, let's see if we can get this sorted out. So we're just going to do very simple stuff in this machine, because this is all this is doing is updating the state. And we're going to want this to be handled here. And H rollover. Yeah. Okay. State next counter equals counter next H active equals active next. Oh, I seem to have that's all that really matters, right? Oh, and we need HSync. Next. Zero. Maybe do another block and move those into the other block. Okay, so now we're going to do another process, and this is the fun one. We're going to do everything that changes. So there's our sensitivity list. In our sensitivity list, we need to state everything that we care about. So the state and the counter is used. We don't care about active, we don't care about that. I think it's just going to be state and counter. That's the only thing that is going to affect the operation of this. How we begin. And now we want to do a case statement. So first off, we should assign some defaults. So HSync next is 0. H rollover next is 0. And H active next is 0. And next counter is going to equal counter plus 1. And now we can do our case statement. Based upon state cases, and we'll just do n case. In case, yeah. So we're going to say sync so we need a win. When sync is high, we're going to have HSync be a 1. And if counter I'm going to check something real quick. We just said if counter equals that value. So if counter equals def h sync, then and if next state will be BP for backwards. Did these guys come in as standard logic vectors? Well, that's annoying. I'll do I guess the easy solution. when BP. What we're gonna do here, we're just determining when the counter ends for this, right? So we're just gonna say BP. Oh, one important thing if we're doing all this fancy stuff is next counter needs to be others. Like that. Maybe we might be able to do add H. Oh, why don't we bring these things into these blocks, because these blocks are the ones using them. H active. H active. Actually, just copy this one. H active. We're going to copy Control C, Control V. H active. Active. And H active next. So that one taken care of. We got this thing taken care of. And now we're gonna do front porch. And front porch is just going to go back to sync. And when it does go back to sync, we want H rollover to go high. Okay. So we got our horizontal state machine done. We're gonna add in the vertical system, and then we just gotta work on the pixel data, which should be easy. But yeah, there you go. So I think that's gonna be it for this stream. We'll copy and paste this one down here. Maybe do some quick edits, like grab this state machine. Boom. And the cool thing about blocks, it makes copy and paste large sections of code very easily. And then we can figure out how that works. So yeah, we just gotta do some edits on how the counter increments. So we just want to increment the counter on a rollover, and then we just gotta change some defines, and we'll do that next time. And change all these values starting here. Start here. Okay, so we'll start there, go through and finish this up, and then we should be good with our timing core for our DVI. Okay, tell me if you guys want this on a repository or something. At the moment, I'm just adding the videos to YouTube, but I can put all these files in a repository at some point. Well, that's it. It's been a good hour. I should be on again tomorrow at 7:30, and feel free to drop by, add some suggestions, some questions, anything. Okay, bye.